Right now, as you sit there listening to this, your head is actually aging slightly faster than your feet.
Which is just, I mean, it's wild to think about.
It really is. It's a microscopic difference, right? Measured in like fractions of a nanosecond, but it is an absolute measurable physical reality. Gravity is literally pulling time apart across the length of your body.
Exactly.
So, welcome to the deep dive. Today, my mission is to completely dismantle the thing you probably look at, I don't know, 50 times a day, which is the clock.
Oh, yeah. We are so dependent on it.
Totally. You wake up, your phone tells you exactly how many minutes you have to shower, grab coffee, commute. You build your entire existence around schedules and calendars.
Right. We treat time like it's this piece of concrete engineering, like it's the unquestionable foundation of reality.
Exactly. But today, I'm taking you on a journey through a stack of research centered around this fascinating text, The Arrow in the Abyss, Modern Physics of Time, to show you why that ticking clock on your wall is completely lying to you.
Yeah, it really is.
Because here's the grand irony, right? Scientists, like the most brilliant minds working in modern physics, do not fundamentally know what time is.
No, we really don't.
They don't know why it moves forward, and they increasingly suspect that the way you and I experience it is, well, it's nothing but a persistent neurological illusion.
It's a persistent illusion. I love that phrasing.
Right. So to help me translate the absolute madness of modern cosmology and, quantum physics into something we can actually wrap our heads around, I'm joined by the perfect analytical mind.
Well, I appreciate that introduction. And it really is the ultimate blind spot in human knowledge, isn't it?
Oh, absolutely.
We measure time with atomic precision now, down to the octosecond.
Mm-hmm.
Yet we are essentially measuring a phantom.
A phantom, yeah.
Yeah, the deeper you look into the actual mechanics of the universe, the more you realize that our everyday intuitive experience of time, like that relentless river flowing from the past into the future, it just doesn't seem to exist at the fundamental level of reality.
Okay, let's unpack this. Because honestly, I need to wrap my head around how something so painfully real to you and me could be a phantom.
Sure.
To get there, I think we have to start with the baseline. How did we used to think about time, before modern physics came along and basically broke everything?
Well, we have to go back to Isaac Newton in the late 17th century.
Okay, classic Newton.
Right. Newton codified the classical view of time, which, ironically enough, is the exact view almost everyone listening to this still relies on in their daily lives.
Oh, for sure.
He described time as a universal, absolute clock. He explicitly wrote that absolute time flows equably without relation to anything external.
So in Newton's mind, time was essentially the stage that the universe was built on, like a rigid backdrop.
Exactly.
So if I snap my fingers right now, that exact moment happens simultaneously for me, for someone in Tokyo, and for like an alien sitting on a rock in the Andromeda galaxy.
Right, a cosmic metronome. In the Newtonian universe, space and time are completely independent of each other.
Like two different things entirely.
Yeah. Space is just an empty 3D box where things happen, and time is the invisible clock ticking at the exact same rate for everyone, everywhere, forever, regardless of what they are doing.
And I mean, for a couple of hundred years, that math worked perfectly.
It did. It predicts how cannonballs fly and how planets orbit. It's great.
Right.
But then, in the late 1800s, scientists started studying light, specifically electromagnetism. And the cracks in Newton's perfect clock started to show.
Because of the speed of light, right. The text makes a massive point about this. But I'll be honest, why does measuring the speed of light suddenly force us to rethink time?
It's a great question.
I just don't inherently see the connection between a moving photon and a clock.
It's not intuitive at all, which is exactly why it took someone like Albert Einstein to figure it out.
Fair enough.
The problem was that James Clerk Maxwell's equations for electromagnetism show that light always travels at a constant speed, about 186,000 miles per second in a vacuum.
Always?
Always. But under Newton's laws, speeds are additive.
What do you mean by additive?
Like if you throw a baseball at 50 miles an hour while standing on a train that's also moving at 50 miles an hour, a person standing on the ground sees that baseball moving at 100 miles an hour.
Right, 50 plus 50. Standard common sense.
Exactly. But light doesn't do that.
It doesn't.
No. If you shine a flashlight from the front of that speeding train, a person on the ground doesn't measure the light moving at the speed of light plus the speed of the train.
Oh, weird.
They measure it moving at exactly the speed of light.
Yeah.
And the person on the train also measures it at the exact same speed.
So everyone, everywhere, no matter how fast they're moving, measures the speed of light as exactly the same constant number. Wait, okay. If speed is just distance divided by time,
Right.
and two people moving at completely different speeds are measuring the exact same speed for that beam of light, well, something else in that equation has to be breaking.
And that was Einstein's massive leap in 1905 with special relativity. If the speed of light is absolute and unchangeable, then space and time cannot be absolute. They have to be the things that are flexible.
Wow.
To keep the speed of light constant for every observer, the actual passage of time has to slow down for the person moving faster, and the physical space they are moving through has to literally contract.
Okay, so that is the concept of time dilation. Let me try an analogy here. Tell me this tracks.
Let's hear it.
It's like we always thought the universe was running on a giant cosmic grandfather clock that everyone could see and agree on.
Right, the Newtonian view.
But Einstein proved we're all actually wearing personalized smartwatches, and those watches are actively speeding up or slowing down depending on how fast we're physically running.
It's a really good analogy for the subjective experience of it, but here is where that metaphor actually falls a little short. Because a smartwatch implies a mechanical device that might just be, running slow.
Like a glitch.
Right. But Einstein wasn't saying your clock is broken.
Yeah.
He was saying the fundamental fabric of reality itself is stretching. A biological process, a chemical reaction, the decay of a subatomic particle, every single metric of change slows down.
It's terrifying.
And it's not just time. To keep the speed of light constant, the physical distance you are traversing literally shortens.
So the space itself shrinks.
Yes, your smartwatch slows down, but the physical ruler in your pocket also shrinks. Space and time are not separate things anymore. They are a single, malleable, four-dimensional structure. Space-time.
Space-time. Okay, so speed warps this fabric, slowing down time.
Yes.
But earlier I mentioned gravity pulling time apart across my body. That's general relativity, right? Einstein's follow-up theory.
That's great, 1915.
So how does mass come into play here?
Well, a decade later, Einstein realized that gravity wasn't some mysterious invisible tether pulling planets together the way Newton thought about it.
Okay.
Gravity is just the curvature of space-time. Think of space-time as a trampoline.
Okay, I'm picturing it.
If you place a heavy bowling ball right in the middle, it creates a deep dip. And that dip dictates how things roll around it.
Right, the marbles would spiral inward.
Exactly. Massive objects, stars, planets, you, me, we all warp the space-time fabric. And here's the real kicker.
What's that?
The deeper you are in that gravitational well, the slower time passes relative to someone who is further out.
So because I'm standing on the surface of the Earth, I am deeper in Earth's gravity well than, say, someone flying overhead in a 747.
Yep.
So my time is literally ticking slower than theirs.
Yes, that's why your feet, being closer to the center of the Earth's mass than your head, experience slightly more gravity.
So time ticks microscopically slower for my feet.
Exactly. Now, on Earth, this effect is, negligible for biology. You won't notice it.
Right.
But if you were to orbit incredibly close to a supermassive black hole, which creates an unimaginably deep well in space-time, you could spend a few hours there, return to Earth, and find that hundreds of years have passed for the rest of human civilization.
See, that always sounds like pure Hollywood science fiction to me, like Interstellar.
Oh, Interstellar got the physics very right on that.
Yeah. But the source text is absolutely adamant that this isn't just blackboard math. We have actually proven this.
We prove it every single day. The most ubiquitous example is the global positioning system.
The GPS.
The GPS running on your phone right now.
Right. The text breaks down this GPS paradox, and I really want you to walk me through the specific mechanics of this, because it's just fascinating how engineers had to basically concede to Einstein to make Google Maps work.
It's a brilliant real-world application.
Yeah.
So GPS relies on a constellation of satellites orbiting the Earth, right?
Yeah.
Because they are in orbit, they are moving incredibly fast relative to you standing on the ground, around 14,000 kilometers per hour.
That is fast.
Very fast. And according to special relativity, because they are moving so fast, their onboard atomic clocks should tick slower than a clock on the ground.
Okay, time dilation from speed.
Right. They actually lose about 7 microseconds a day just due to their speed.
Okay, 7 microseconds slower. But wait, they are also floating out in space, far away from the Earth.
Exactly. They're about 20,000 kilometers above the Earth's surface.
So less gravity.
Significantly less gravity. And according to general relativity, Because they are in a weaker gravitational field, their clocks should tick faster than ours.
Because they aren't as deep in the trampoline dip.
Exactly. And this gravitational effect causes them to gain about 45 microseconds a day.
Okay, so you have these two bizarre effects physically fighting each other. Speed is dragging the clock backward by 7 microseconds, but the weaker gravity is pushing the clock forward by 45 microseconds.
Which nets out to an extra 38 microseconds a day.
I mean, 38 microseconds sounds completely trivial.
It sounds like nothing. But GPS calculates your exact position based on the time it takes a radio signal traveling at the speed of light to reach your phone from the satellite.
Oh, I see.
So if the engineers didn't program Einstein's relativity equations into the satellite software to artificially slow those clocks down and offset that 38 microsecond drift.
How badly does the system break? Like, what happens?
Within just one single day, the navigation system would be off by about 11 kilometers.
You're joking. 11 kilometers in one day.
Yep, your map app would think you were driving through the middle of a lake. Within a week, the entire global GPS network would be completely useless.
That is mind-blowing.
So the fact that you can find the nearest coffee shop is absolute, daily proof that time is a flexible, bendable dimension that warps based on speed and mass.
Okay, wow. You've successfully shattered my Newtonian clock.
Glad to help.
The rate of time is utterly subjective. But, this creates a massive paradox in my mind, which brings us to the next major conceptual block in the source material.
Okay, let's hear it.
If time is this flexible, bendable fabric, why am I trapped moving in only one direction?
The arrow of time.
Right, because space is flexible and I can walk forward, backward, left, or right in space. If time is woven into space, why can't I walk backward in time? Why do we collectively experience it as a relentless one-way street?
It's one of the most profound questions in physics. Even though the rate of time's passage can stretch or compress, the direction appears strictly rigid.
Yeah, you remember yesterday, but you don't remember tomorrow.
Exactly. You watch a glass shatter on the floor, but you never, ever see the shards spontaneously levitate, reassemble perfectly, and jump back into your hand.
But why not? If the fabric of the universe allows time to stretch, what invisible law is acting like a ratchet, just preventing it from clicking backwards?
Well, the leading explanation doesn't actually come from relativity at all. It comes from thermodynamics.
Thermodynamics?
Yes. Specifically, a concept developed in the 19th century called entropy. It is arguably the ultimate governing law of the macroscopic universe.
Entropy. Okay, I remember high school chemistry treating entropy just as a measure of, messiness or chaos.
That's a standard textbook definition.
The source text talks about ice melting and clean rooms getting dirty. But how does messiness dictate the fundamental flow of time?
To understand why it dictates time, we really have to look at what entropy actually is mathematically, which was brilliantly formulated by the physicist Ludwig Boltzmann.
Okay.
He realized that entropy isn't just some vague concept of chaos. It is a strict measure of probability.
Probability?
Yes. It's about counting the number of microscopic arrangements, what he called microstates, that result in a specific macroscopic appearance, or macrostate.
Okay, you just lost me a bit. What is the difference between a microstate and a macrostate? Can you give me a tangible example?
Sure, let's use coins. Imagine I give you 100 coins and ask you to just flip them all onto the floor.
Okay, 100 coins on the floor.
The macrostate is what you see when you look down. The overall ratio of heads to tails. A microstate is the specific individual state of every single coin. Coin number 1 is heads, coin number 2 is tails, and so on.
Got it. The big picture versus the individual data points.
Exactly. Now, how many ways can you get a macrostate of exactly 100 heads?
Just one, right? Every coin has to be heads.
Right. There is only exactly one microstate that achieves that. Every single coin must be heads. It is a highly ordered, extremely low entropy state.
Okay.
But how many ways can you get a macrostate of roughly 50 heads and 50 tails?
Oh, a lot.
Billions. There are billions of different combinations, billions of different microstates that result in that messy, mixed-up macrostate. That is high entropy.
So if I scoop up those 100 coins, shake them in a box, and dump them out again, the odds of them landing perfectly on 100 heads again are practically zero.
Almost impossible.
Not because physical laws forbid it, but purely because of the overwhelming statistics. There are billions of ways to be messy and only one way to be perfectly neat.
Exactly. The second law of thermodynamics dictates that in any closed system, entropy tends to increase simply because there are overwhelmingly more ways for a system to be disordered than ordered.
That makes total sense.
A brand new deck of cards ordered by suit has incredibly low entropy. If you shuffle it, you move it to a high entropy state.
And nature always shuffles the deck. Always. The ice cube melts because there are vastly more ways for water molecules to arrange themselves as a liquid puddle than as a rigid crystal lattice.
And this transition, this statistical drift from order to disorder, is what we perceive as the flow of time.
Yes.
So time's arrow is essentially just the universe inevitably shuffling its deck of cards.
That's a great way to put it. The burning of a star, the ticking of a clock, the firing of the neurons in your brain forming a memory, all of these processes require energy to be dispersed, which increases the overall entropy of the universe.
Wow.
Without entropy increasing, nothing would happen. Time as a sequence of events would cease to exist entirely.
But wait, I have a major point of contention here based on the text, and this honestly blew my mind when I read it.
Lay it on me.
The source clearly states that at the microscopic fundamental level, the laws of physics are time-symmetric.
Yes, they are.
They do not care about time's direction. If I film two billiard balls colliding on a table, the physics equations govern how energy transfers and how they bounce off each other.
Standard Newtonian mechanics. Right. But if I play that video in reverse, the motion of those billiard balls still looks completely physically valid. The equations of motion work perfectly both ways.
They do.
So if the microscopic building blocks of reality don't have an arrow of time, how does the universe suddenly get one just because things get bigger?
That is Loschmidt's paradox.
Yeah.
It was a massive thorn in Boltzmann's side during his lifetime.
We can see why.
How do you derive macroscopic irreversibility from microscopic reversibility? It seems like a total contradiction.
Right.
But the answer scales directly from what we just discussed about probability.
How so? Walk me from the two billiard balls up to, say, that shattered glass we talked about.
Okay, if you have just two atoms bouncing off each other, time's arrow essentially doesn't exist. Forward, backward, the math is completely identical.
Okay.
But a glass is not two atoms. It is trillions upon trillions of interacting atoms.
Right.
When a glass falls off a table and shatters, it's not just the glass breaking. The kinetic energy of the fall is dispersed into the floor, creating heat. Sound waves vibrate the air molecules in the room. Chemical bonds in the glass snap, releasing tiny amounts of energy.
So it's insanely complex.
Extremely. The localized, ordered energy of the intact glass is scattered into an unimaginably complex, high-entropy microstate.
It scatters completely into the environment.
Yes. Now, the fundamental laws of physics say that every single one of those microscopic interactions is technically reversible.
Wait, really?
Yes. The heat could extract itself from the floorboards. The sound waves could bounce off the walls and perfectly converge back onto the shards of glass.
That's crazy.
The air molecules could perfectly align to push the shards back together and propel the glass back up onto the table.
So you're telling me it is not physically impossible for a shattered glass to spontaneously unbreak?
It is not expressly forbidden by the microscopic laws of physics? No. However, the statistical probability of trillions of random scattered air molecules and heat vibrations perfectly coordinating their trajectory simultaneously to reverse that process.
The odds are zero.
The odds are so astronomically small that it would likely take far, far longer than the current age of the universe for it to happen even once.
So it's technically possible, just statistically absurd.
Precisely. And that statistical absurdity is what creates the rigid arrow of time. We are trapped moving in one direction because to go backward would require a miraculous, statistically impossible decrease in entropy.
Okay, so entropy acts as the statistical iron law that dictates the direction of events. It gives us the sensation of the present becoming the past.
Exactly.
But as the source material brilliantly pivots to point out, this completely solves one problem while immediately creating a much, much bigger one.
Oh, really good.
It creates a terrifying paradox about the origin of the universe.
It forces us into a very uncomfortable logical corner. If we know that the universe is constantly moving from order to disorder, if tomorrow is always messier than today, then we can just run that logic backward.
Yesterday must have been more ordered than today.
Yes, 1,000,000 years ago it was even more ordered.
And if we keep walking backward, winding the clock back 13.8 billion years all the way to the Big Bang, we arrive at a universe that must have had an incredibly, unbelievably low entropy.
Yes, it must have been perfectly ordered.
And that is the problem, right?
That's the past hypothesis. As we established, low entropy states are incredibly rare and improbable. High entropy, messy states are overwhelmingly more likely.
Right, the 100 coins landing on heads is rare.
Exactly. So if the universe started as a tiny, unimaginably hot, dense point of energy, Statistical mechanics strongly suggests it should have been born in a state of maximum disorder.
Actually, the text says exactly that. It says, if the universe had started in maximum disorder, there might be no obvious arrow of time at all.
Right. If the Big Bang produced a completely homogeneous maximum entropy soup, it would be like a fully shuffled deck of cards.
You can keep shuffling it, but it doesn't change.
Exactly. You can shuffle it forever,
Yeah.
but nothing interesting would ever happen.
Yeah.
Gravity couldn't pull gas clouds together to form stars because forming a star is a localized decrease in entropy.
Oh, wow.
No planets would form,
Hmm.
no complex chemistry, no biology, and certainly no brains to perceive the passage of time.
I want to just pause on this because this is where the sheer scale of the mystery really hit me.
It's heavy.
It's like walking into a casino and watching a roulette wheel land on the number 0 a billion times in a row.
That's a great visual.
Technically, by the strict laws of probability, every spin is independent, so it could happen by pure random chance. But if you actually saw that happen, you wouldn't just shrug and say, wow, crazy odds.
No, you definitely wouldn't.
You would immediately assume the game is rigged. You'd assume there is a hidden magnet or a deeper mechanism you don't understand that is actively forcing the wheel to start in that exact state.
I wouldn't call it rigged, but I'd absolutely look for the magnet. In fact, the physicist Roger Penrose actually calculated the odds of our universe naturally, starting in the low entropy state required to produce our current reality by pure random chance.
Oh, really? What was the number?
The number he came up with was 1 in 10 to the power of 10 to the power of 123.
I don't even know how to visualize a number that large.
You can't. If you wrote a 0 on every single proton and neutron in the entire observable universe, you would run out of particles long before you finished writing that number.
That is insane.
It's practically 0. It tells us that our universe did not start in this state by random chance. There must be a hidden mechanism, some profound physical law we have not yet discovered, that forced the early universe into this incredibly orderly, pristine condition.
So what are the current theories? What could possibly act as that cosmic magnet? Because the text briefly outlines a few frameworks attempting to explain the beginning.
Well, theoretical physicists are essentially throwing darts at the board right now because we have no way to actually observe before the cosmic microwave background.
Right.
But there are compelling mathematical frameworks. One is cyclic cosmology, or bounce cosmology.
How does that one work?
This suggests that the Big Bang wasn't the absolute beginning of everything, but rather a transition point.
Okay.
A previous universe expanded, eventually collapsed back in on itself, and the intense quantum dynamics of that big crunch essentially reset the entropy clock, bouncing back outward as our Big Bang.
Like an infinite cosmic lung, just breathing in and out.
Exactly.
What else? What's another theory?
Another major theory relies on eternal inflation in the multiverse.
The multiverse.
Yeah. This theory proposes that space is constantly expanding incredibly fast, but little pockets occasionally slow down and stop inflating, crystallizing into these bubble universes.
Okay, so our universe is just one of an infinite number of bubbles.
Right.
But how does that solve the entropy problem?
It relies on the anthropic principle. In a multiverse with infinite bubbles, the vast majority of those universes might be born with maximum entropy.
So they're just dead, messy soup.
Exactly. They are dead, timeless voids where nothing happens. But given infinite chances statistically, a tiny fraction will randomly form with incredibly low entropy, just by sheer fluke.
And because complex life requires low entropy to evolve, we can only ever find ourselves living in one of the freak accident low entropy bubbles.
Precisely. We see a highly ordered universe because if it wasn't highly ordered, we wouldn't be here to see it.
Wow, we are marveling at our own existence, totally oblivious to the trillion dead universes right next door.
That's the idea. But again, these are highly speculative models. The why of the Big Bang's perfectly pristine low entropy state remains one of the deepest open wounds in modern cosmology.
Yeah, I mean, we are basically living in a universe that started as a meticulously organized neat freak, and all of human history is just us surfing the long, slow wave of its expanding messiness.
That is a very poetic and very accurate way to put it.
So let's pull these threads together. Einstein says the rate of time is just a flexible illusion dependent on your speed and gravity.
Yes.
Thermodynamics says the flow of time is just a statistical illusion based on things getting messier.
Right.
If both the rate and the flow of time are essentially mechanical illusions, does the present moment even exist? Because the text dives into a concept that fundamentally challenged my entire perception of reality.
You were referring to the block universe. And yes, this is where physics takes our deepest, most intimate, human intuition and just completely dismantles it.
We all intimately feel the flow of time, right? I'm speaking these words right now. The words I said 10 seconds ago are gone, completely vanished into the past.
That's how it feels.
The words I will say 10 seconds from now do not exist yet. There's only this razor-thin sliver of reality called now. That is the human experience.
Absolute.
But the source material asks bluntly, does time actually flow? And then it just answers no. The block universe says something entirely different.
The block universe, which is the natural philosophical conclusion of Einstein's relativity, proposes that all moments in time, the past, the present, and the future, exist simultaneously.
Wait.
They are all equally real.
I need you to explain how that can possibly be true. How can my future already exist?
It stems directly from what we discussed earlier about relativity and the speed of light. Because time is relative to the observer's speed and gravity, there is no universal clock, right?
Right.
Therefore, there is no universal now. Physicists use a famous thought experiment called the Andromeda paradox, or the Reddick-Putnam argument, to illustrate this perfectly.
Walk me through this Andromeda paradox.
Imagine two people walking past each other on a street here on Earth.
Mm-hmm.
Person A is walking north. Person B is walking south.
Okay.
Because they're moving relative to each other, their planes of simultaneity, which is their definition of what events are happening now across the universe, are slightly tilted relative to one another.
Okay, so their smartwatches are ticking at microscopically different rates because they are moving different directions.
Right. Now, point their perspectives toward the Andromeda galaxy, which is 2.5 million light years away.
That's far.
Very far. For person A, their slice of now intersecting with Andromeda might include a council of aliens debating whether to launch a fleet toward Earth.
Okay, alien debate happening now.
But for person B, walking the exact opposite direction, their slightly tilted slice of now intersects Andromeda a week later in the alien timeline.
Wait, a whole week?
Yes, because at that massive distance, a microscopic tilt in the angle of now results in a massive gap in time. So for person B, the fleet has already launched.
So depending on which way you're walking down the street, an event millions of light years away has either not happened yet or is already history.
Precisely. Because both person A and person B are experiencing a completely valid physical reality, both states of the Andromeda galaxy must be equally real.
Oh my God.
And if an event in my future can be in your past simply because we are moving at different speeds, then the future must already be out there.
The math demands it.
The past must still be back there. Time is not a sequence of things coming into existence and fading away. The entire universe is a giant four-dimensional block of space-time.
I originally thought about this like a DVD movie.
Oh, that's an interesting way to picture it.
Like the entire film, the opening scene, the climax, the end credits, exists simultaneously encoded on the physical disc. The data is all there at once.
Right.
But our consciousness is just the laser inside the DVD player, reading one single frame at a time. And we stubbornly call the specific frame being illuminated by the laser now.
That analogy is close, but I actually want to push back on it slightly.
Okay, where does it break down?
The DVD metaphor implies there's an external laser, some external mechanism driving you through the movie frame by frame.
Right, pushing me forward.
In the block universe, there is no external laser.
Yeah.
Your entire life, from birth to death, is embedded as a static four-dimensional worm weaving through the block.
Oh.
Yeah. Your consciousness at age 10 is forever located at that specific coordinate in space-time. Your consciousness at age 80 is forever located at its coordinate.
So there is no moving through it at all?
Not physically, no.
Yeah.
Now it's just an evolutionary trick.
The trick.
The brain is essentially an information processing engine. It constantly receives sensory input, catalogs memories of previous inputs, and uses those patterns to predict future inputs.
Okay, survival instinct.
To make sense of causality, to understand that touching a hot stove causes pain, the brain organizes this data sequentially.
Right.
The feeling of now is just a localized consciousness at any given point in the block, accessing the memories written behind it and anticipating the void ahead of it. The flow of time is a psychological phenomenon, not a physical one.
It just completely strips away the concept of free will, in a sense.
It certainly feels that way.
If my future is already a fixed coordinate in the space-time block, my death is already sitting there waiting for my consciousness to reach that temporal coordinate. That is terrifying.
It forces a massive reevaluation of determinism, for sure. But from a purely physical standpoint, it's also quite profound. It means nothing is truly lost.
What do you mean?
The past isn't erased. It is a permanent structural element of the universe.
Wow. But, you know, this naturally leads to the science fiction holy grail,
Time travel.
Time travel. If the universe is a 4D block and all moments exist permanently, like coordinates on a map, can I travel to different coordinates?
It's the logical next question.
The text explicitly explores time travel and the edges of reality. So let's separate the Hollywood fantasy from the actual mathematical reality.
Let's start with the easy one. Time travel into the future is a 100% proven scientific fact. We do it constantly.
Right, through time dilation. Like if I get in a ship, accelerate to 99% the speed of light, fly around for a year and come back, centuries will have passed on Earth. I have traveled to the year 2500.
Exactly. Forward time travel is purely an engineering problem.
Yeah.
You just need enough energy to go fast enough, or you need to go orbit a black hole.
Okay, but what about backward? Navigating to a coordinate in the block universe that is behind your current position. That is where the math starts screaming.
Does Einstein's math explicitly forbid going backward?
That is the most frustrating part. No.
It doesn't.
No. General relativity actually permits backward time travel. The equations allow for geometries of space-time where paths loop back onto themselves. These are called closed time-like curves.
The source mentions wormholes as a potential mechanism for this. How would a wormhole act as a time machine?
Well, a wormhole is a theoretical tunnel connecting two distant points in space-time. The physicist Kip Thorne demonstrated mathematically that if you had a wormhole and you kept one mouth of it stationary on Earth, but put the other mouth on a spaceship, moving it near light speed.
Oh, the moving mouth would experience time dilation. It would age slower than the stationary mouth.
Precisely. The two mouths of the tunnel become completely desynchronized in time.
Wow.
So if you step through the stationary mouth on Earth, you might emerge from the moving mouth 10 years in the past. So the math actually allows it. Why don't physicists think we can actually do it?
Because it completely shatters causality. It creates insurmountable logical paradoxes.
Like the grandfather paradox.
Exactly, or the birth paradox. If you travel back through that wormhole and successfully prevent your parents from ever meeting, then you were never born.
Right.
But if you were never born, you cannot enter the wormhole to prevent them from meeting.
Right.
So they do meet, and you are born, so you do enter the wormhole.
Huh.
It is a logical short circuit.
How does physics resolve a short circuit like that?
There are a few theories. The Novikov self-consistency principle suggests that the laws of physics will actively prevent a paradox.
Like Final Destination?
Kind of. If you travel back, the gun will jam, or you'll slip on a banana peel. Your actions in the past are already baked into the history that created you.
You cannot change the block universe.
Right. You can only fulfill your role in it.
Which perfectly aligns with the static 4D block concept. The DVD is already pressed. You can't edit a scene you're already in.
Exactly. However, many physicists, like Stephen Hawking, suspect there is a yet undiscovered law of physics, what Hawking called the chronology protection conjecture, that prevents closed, time-like curves from forming in the first place.
So the universe just says no.
The universe might simply forbid backward time travel at a quantum level just to protect the timeline.
So we hit a paradoxical wall when we try to travel backward, but there is another massive wall the text brings up.
Which one?
Not traveling back in time, but trying to look back to the origin of time itself. The text asks, could time have existed before the universe?
This is where human language completely fails us.
Yeah, it really does.
The standard model says the universe began 13.8 billion years ago with the Big Bang. But people always picture the Big Bang as an explosion happening inside an empty room.
Right, like a firework going off in the dark.
That is wrong. The Big Bang was an explosion of the room. Space and time emerged together in that specific moment.
So, if Einstein proved that space and time are inextricably woven into space-time, does that mean before space expanded, time literally did not exist?
Yes. And the source text provides what is probably the best analogy in all of cosmology for this.
I loved this analogy.
Asking what happened before the Big Bang is like standing at the North Pole and asking which way is north.
Oh, I see. Because everywhere you point is south.
Exactly. North is a coordinate on the Earth's surface. Once you reach the absolute pole, the concept of north loses all mathematical and physical meaning.
You've run out of globe.
You have reached the boundary of the coordinate system. Similarly, time is a coordinate within our universe. If time began at the Big Bang, the word before has no meaning whatsoever.
Because before is a temporal concept.
Right. You cannot apply a time-based word to a state of non-existence of time.
To ask what time it was before time existed is a nonsense question. It's structurally impossible.
In the standard framework of general relativity, yes. Now, Stephen Hawking and James Hartle tried to tackle this mathematically with the no-boundary proposal.
What's that?
They used imaginary numbers for time to smooth out the origin point, suggesting the universe has no sharp beginning, just a gradual emergence of space-time.
Imaginary time.
Yeah, but again, we're dealing with extreme mathematics where our daily intuition is completely useless.
Why do we keep hitting these walls? We hit a wall with time travel paradoxes. We hit a wall with the Big Bang and the North Pole analogy.
It's a pattern.
The source material suggests that the reason the greatest minds in history get stuck here is because our two fundamental rule books for how reality works are completely incompatible.
We have arrived at the ultimate crisis in modern physics, the problem of quantum gravity.
Let's get into it.
As we've discussed, we have two incredibly successful frameworks. First, Einstein's general relativity, which describes the macro universe, gravity, stars, the 4D block.
Right.
And in this rulebook, time is dynamic. It bends, it warps, it is a physical participant in reality.
But the second rulebook, quantum mechanics, describes the microuniverse. Atoms, subatomic particles, quantum fields.
And quantum mechanics is arguably the most rigorously tested and accurate theory in human history.
That's why we have computers.
It gave us lasers, microchips, MRI machines. But here is the fatal flaw. Quantum mechanics treats time completely differently than relativity does.
The text mentions that quantum mechanics treats time as an external parameter. What does that actually mean mechanically? Why does the microscopic world disagree with Einstein?
Well, in quantum mechanics, particularly in the famous Schrödinger equation, time, the variable t, is just a mathematical variable ticking away in the background.
Okay.
It acts exactly like Newton's old, absolute, unbending clock. In quantum equations, events unfold within time, but they do not affect time.
Time doesn't bend for a quantum particle.
No. Time doesn't bend or warp around it. It's just an external metronome keeping the beat for the math to work.
Okay, I see the collision course here. Relativity says time is a pliable fabric woven with space. Quantum mechanics says time is a rigid, invisible background metronome.
Yes.
They literally describe two completely different realities.
And this is fine as long as you keep them separate. You use relativity for big, heavy things and quantum mechanics for tiny, light things.
But what happens when you have something that is both incredibly massive and incredibly tiny?
Like the center of a black hole.
Ah.
Or the precise moment of the Big Bang.
Oh, right.
Exactly. When physicists try to smash the equations of general relativity and quantum mechanics together to understand a black hole, the math literally explodes.
Explodes how?
It breaks down and gives nonsensical answers, like infinite probabilities, which are physically impossible. The two rule books cannot coexist.
So we need a new rule book.
This is why thousands of physicists are desperately searching for a theory of quantum gravity, a unified theory that bridges the macro and the micro.
And the source text points out that in the pursuit of quantum gravity, physicists might have stumbled onto the most radical, paradigm-shifting idea of all. It's a section titled, "Is Time an Illusion?"
This is the absolute bleeding edge of theoretical physics. When physicists try to quantize gravity using frameworks like the Wheeler-DeWitt equation, something terrifying happens to the math.
What happens?
The variable for time entirely drops out of the equation.
Wait, what? The equation for the fundamental state of the universe just doesn't include time.
It's gone. The math describes a perfectly static, timeless web of probabilities, which forces us to ask the ultimate question.
What if time isn't fundamental?
Right. We've always assumed time is a basic building block of reality, like a proton or the dimension of length. But what if, at the absolute deepest layer of quantum reality, time simply does not exist?
But if time doesn't exist at the bottom layer, then why is my alarm clock going to ring tomorrow morning? Where does the time that we experience actually come from?
The leading proposal is that time is emergent.
Emergent time.
The source material provides a stunning analogy here. It suggests that time emerging from timeless quantum mechanics is exactly like temperature emerging from the motion of atoms.
Explain that analogy, because I think grasping this is the key to the whole mystery.
Think about a cup of hot coffee. When you touch the mug, you feel a property we call temperature.
It's hot.
It feels like a fundamental inherent property of the coffee. But if I give you a microscope powerful enough to isolate one single water molecule bouncing around inside that coffee, and I ask you, what is the temperature of this single molecule? What is the answer?
Well, a single molecule doesn't have a temperature. It just has kinetic energy. It has speed.
Precisely. Temperature does not exist at the microscopic level. It is not a fundamental property of a particle.
Okay, I'm following.
Temperature is a collective macroscopic behavior. It is an emergent property. It is what our macro-level skin feels when billions of microscopic molecules are vibrating and bouncing against us.
So temperature emerges from the statistical average of timeless, temperatureless interactions.
And theoretical physics is suggesting that time itself is doing the exact same thing.
Yes.
Physicists like Carlo Rovelli, working on loop quantum gravity, propose the thermal time hypothesis.
Thermal time.
They suggest that at the Planck scale, the most granular, microscopic level of reality, there are no ticking clocks, no past, and no future.
Just static data.
There's only a vast, timeless network of quantum entanglement, particles interacting, sharing information, updating their states relative to one another.
Just raw, timeless data relationships.
Exactly. But when you zoom out, when you string trillions of these quantum interactions together, a macroscopic pattern emerges.
Like the heat of the coffee.
A sequence of before and after is generated by the transfer of quantum information. And our massive macroscopic brains render that sequence as a timeline.
Change at the quantum level creates the illusion of time at the human level.
We experience the temperature of quantum entanglement, and we call it time.
That is deeply staggering. It means time isn't a river we are floating in. It is a secondary byproduct of quantum math.
Yes.
It is an illusion rendered by the macroscopic brain so we can process causality without going entirely insane.
If emergent time is proven true, it will be a paradigm shift far greater than Einstein overthrowing Newton. It means our entire conscious existence is basically a user interface overlaying a timeless quantum reality.
What a profound unraveling of everything we think we know.
Yeah.
Let's do a quick recap of the staggering journey this text has taken us on today.
It's been a lot.
We started with Newton's comforting, unbending universal clock. Then Einstein came along with the sledgehammer, proving that the speed of light is the only constant, which forces time to dilate and warp based on how fast you move and how much gravity is pulling on you.
Then we confronted thermodynamics. The concept of entropy showed us that time's one-way flow is really just a statistical probability. It's just the universe moving from a neat microstate to a messy macrostate.
Which pointed us backward to the massive unsolved past hypothesis. The terrifying statistical miracle that the Big Bang started with almost zero entropy, a pristine, neat freak universe that allows us to exist at all.
We explored the dizzying 4D block universe, realizing that the relativity of simultaneity means the past, present, and future all exist simultaneously in a static 4D sculpture.
Our experience of now is just a localized trick of consciousness.
We hit the logical brick walls of closed, time-like curves, realizing we probably can't travel backward without short-circuiting causality.
And we realized asking what happened before the universe began is like asking what is north of the North Pole.
And finally, the ultimate collision, relativity versus quantum mechanics, leading us to the Wheeler-DeWitt equation and the very real possibility that time is just a macroscopic illusion.
An emergent property bubbling up from a timeless quantum foundation, exactly like heat rising from moving atoms.
That's incredible.
Every single heartbeat you feel, every memory you look back on, every anxiety you have about tomorrow relies entirely on a framework that the greatest scientific minds in human history still cannot fully explain or define.
It's humbling.
But I want to leave you with one final, slightly provocative thought to chew on. Something rooted directly in the physical laws of entropy we discussed today.
Oh, where are you taking this?
Well, the source stated clearly, time's arrow relies entirely on the universe moving from order to disorder. Entropy must increase for time to flow.
Right, the shuffling of the deck.
So consider the incredibly far future of our universe, trillions upon trillions of years from now. As entropy relentlessly increases, the universe will eventually reach a state of absolute maximum disorder. Stars will exhaust their fuel and die. The black holes will eventually evaporate into radiation. All heat and energy will dissipate evenly across an infinitely expanding cold void.
The heat death of the universe, maximum entropy.
Right, a completely uniform, unchanging thermodynamic soup. No further heat or energy can be exchanged. Nothing can happen because the universe is already perfectly, maximally messy.
It's a bleak picture.
So, according to the physics of Boltzmann and the arrow of time we just mapped out, when nothing can change anymore, when entropy cannot possibly increase, does the arrow of time literally vanish?
That's the question.
Does time, as a physical concept, effectively die when the universe finally runs out of ways to make a mess?
Well, if time emerges from change, and all change permanently ceases, yes. The logical conclusion is a timeless eternity. Time itself will end.
Something for you to ponder the next time you wake up and stress over the ticking clock on your wall, or when you are rushing through your morning commute. The very thing you are chasing might just be an emergent illusion, a temporary, fleeting feature of a messy universe. Thank you for joining us on this deep dive.